So today we're gonna talk about the simple regression model. Okay, so the name is called simple regression model, but I don't think it's the simplest part of this class, and maybe it's the most difficult part for this class because we will learn a little bit more theoretical stuff about regressions. Okay, it's not very practical, but it reviews the principle of econometrics. So after this part, I may focus more on the practical part of econometrics, how to implement the econometric analysis in especially different softwares. Okay, but today we'll learn a little bit theory. So in general, what we do in the econometric analysis or regression is basically using a variable x to explain another variable y. Okay? So that's our purpose. We want to identify what's the impact of this x variable on the y variable. Okay? So there are several examples. For example, we have mentioned in the last class, suppose we study soybean yield and fertilizer. Okay, we want to know if we, for example, increase 1 unit of fertilizer in the plot, how much soybean yield will be increased. Right? So we want to study the relationship between the fertilizer and the soybean yield. Another example is about wage, the relationship between wage and education. Okay? Suppose we have 1 additional year of education, how much additional wage you can earn. Okay? In the simple linear regression, we assume that the relationship between x and y has a linear functional form. Okay, so this is the linear function. Right? As I said, a linear function. In a linear function, you only have multiplication and the summations. Okay, and there are many alternative names on this y variable and x variable. Okay, so the y variable is sometimes called dependent variable, explained variable, or response variable. Correspondingly, the x variable is called independent variable or explanatory variable or the regressor. Okay? So in econometrics, we assume x and y has this relationship. Okay? But most of the time, we don't know the value of this beta 0 and the beta 1, these parameters. Beta 0 is called intercept, and the beta 1 parameter is called the slope parameter. Okay? So we don't know the parameter of the value of these two parameters, so we use statistical method to infer this or to estimate these values of these parameters, okay, with data. And this U here includes all other terms that affect Y. So here we want to study the relation between Y and X, and very typically in social science and economics. For example, let's go to for example, in the wage equation example, except for education, there are many other factors may affect wage. Right? So this U may contains a lot of other variables. It can be labor force experience, okay? Tenure with current employer, work ethic, intelligence, and so on and so forth. Okay? A lot of other factors that we have that's maybe not of our interest, okay? Or we simply don't have data about those factors. For example, intelligence, okay? Or innate ability. So this U is called error term or disturbance or unobservables. Okay? So these are the basic terminology and the basic form of a simple linear regression model. And most importantly, this beta 1 parameter is what is our focus. Okay? So suppose we have the case that x is changed to x prime, and so because of this change, right, y changed to y prime. Okay, so before the change occurs, we have y equal to beta 0 plus beta 1 x plus u. After this change occurs, we have y prime equal to beta 0 plus beta 1 x prime plus u. Okay? Suppose u is not changing, it holds constant. Okay? Then we have delta y, which means the change in y equals to the y prime minus y. A equals to beta 0 plus beta 1 x prime plus u minus beta 0 plus beta 1 x plus u. Right? So I just write out the expression of y prime and y. Okay? And here we can see that beta 0 and beta 0 cancel out, and we assume that u is not changing. The error term or disturbance term is not changing because it also cancels out. And for this one, we have beta 1 times x prime minus x, and this is the change of x. So it equals to the beta 1 times delta of x. So from this step, we get this one, right? So beta, it turns out that the change of x, so how many, so suppose x is changed by 1 unit, then delta y will change by beta 1 unit. So it measures, it quantifies the effect or the impact of x on y, right? So this beta 1 measures by how much the dependent variable change if the independent variable is increased by 1 unit. Okay? So this is the interpretation of this beta 1 parameter or the slope parameter. And there is a very important assumption we have made here. That is, the u is not changing. That is, delta u equal to 0. Right? So the interpretation only correct if all other things remain equal when independent variable is increased by 1 unit. Okay? So it's very important to hold that when you change x, you can other factors can remain constant. Okay, so that you can identify the effect of x on y. So for many reasons, especially this condition is very difficult. Is very difficult to hold. Okay, in a simple linear regression. So practically, we are not very using simple linear regression very often, okay? But we discuss it for pedagogical reasons. Okay? Simply teach you the principles of regression analysis. Okay? And later we will extend to multiple linear regression and other forms of regression models, so that it can be more useful in terms of identify the effect of, for example, some x variable on y variable. Okay, so we have gone through these two examples. So here, if we look at these two examples, for the first one, this beta 1, for example, in this regression model, beta 1 measures the effect of fertilizer on yield. And it's under the condition that all other factors remain constant. Right? Other factors can be rainfall and quality and the presence of parasites. Okay? So this beta 1 say, if I increase 1 unit of fertilizer, then the yield will increase by beta 1 units. In a way, the equation is similar. This beta 1 measures the change in hourly wage given another year of education, holding all other factors fixed. So if suppose that your education is increased by 1 year, then the wage on average will increase by beta 1. Okay, so this is the meaning of this beta. So it's very often this beta 0 is not very important. Okay, in very rare case we will focus on this intercept. Okay, the most important parameter is this beta 1 here. So we have mentioned that to correctly identify beta 1, the slope parameter, we have to have that to hold the disturbance term or the error term kind of constant. Okay? This constant can be translated to statistics in the form of that in the form of the assumption that the conditional mean of u conditional x equal to 0. Okay? So this expression basically tells you that so no matter how x is changing, it is not affecting the expectation of this u. Okay? U is a random variable. Okay? So if you don't understand conditional mean or other things, you simply remember that this statement basically means that the explanatory variable x here must not contain any information about the mean of the unobserved factors or the disturbance term or the error term. Okay. So if you don't understand the statistics, simply remember this line here. Okay. The meaning actually of this line is basically this one. Okay, it basically tells you that you can change x but holding other factors constant. So in the example of wage equation, it's actually a bit complicated here. So the requirement here, suppose U is a kind of ability, okay? Innate ability. Okay? And in the wage equation, basically we uh, this assumption indicates that education and does not affect ability. Okay, so it requires that, for example, the expectation of one's ability conditional on its education equal to 9 years equal to the expectation of one's ability conditional on education equals to 12 years. Right? So it says that suppose your education is 12 years and the other people have education of 9 years. Your ability should be the same, okay? But apparently, this assumption seems not valid. Okay? Seems not very valid. Typically, if your ability is higher, it is more likely for you to pick or receive more education, right? So in the wage equation, this conditional mean independence assumption is unlikely to hold. And if this assumption is violated, it's actually very difficult to identify this beta 1 because suppose when someone's education is higher, then the ability is also higher, right? So you get a higher wage. But when someone's education is lower, his or her ability is lower as well, so his wage is further lower. Right? So you don't know the increase of wage or the decrease of wage, how much is can be attributed to the education, how much can be attributed to the unobserved factors, for example, innate ability or intelligence. Right? So it's very difficult if we don't have this conditional mean independence assumption. It's very difficult to identify this beta. Um, I will talk about this later, okay, in the second half of the class when we talk about endogeneity issues. Okay, but by far, just remember this is the very assumption for us to run regressions, and you should always address this issue once or if you want to run regression. Okay. On the other hand, the conditional mean independent assumption also implies that the conditional expectation of y equal to beta 0 plus beta 1 times x. Okay? So let me skip this. It's not very important, and I don't want to explain too much. Uh, uh, ex- you know, too much time on spend too much time on explaining what is conditional expectations. Okay? So basically, it means that the relationship between x, y, x and the expectation value of y is a straight line here, and for each x, there is maybe a distribution of y. Okay? So now the question is, suppose now we have a sample of n observations. Okay? So x1, y1 is the first sample, x2, y2 is the first sample, and up to xn and yn. And we use this notation xi, yi to express this sample, to present this sample compactly. Okay? So what we want to do is, we have this data. How can we use this data to estimate beta 0 and beta 1? Okay, so that's our objective. So what we want to do here is to guess beta 0 hat and beta 1 hat for the true value beta 0 and beta 1, such that we define this fitted value yi hat equal to beta 0 hat plus beta 1 hat xi fit. So I from 1 to n fits the data or the sample as good as possible. Okay. That's our purpose. That's how we choose, how we estimate beta 0 and beta 1. Okay, we choose or guess some parameter value beta 0 hat or beta 1 hat for beta 0 and beta 1 respectively, so that the estimated value is pretty close to the true value, right? With the data which is yi, right? As good as possible. So how can we, what does this as good as possible means? So basically, we first define the regression residuals, okay, which is ui hat equal to yi minus yi hat, and y hat equal to beta 0 hat plus beta 1 times xi. So this equals to yi minus beta 0 hat minus beta 1 hat xi. Right? And then we minimize the sum of squared regression residuals, okay, by choosing beta 0 hat and beta 1 hat. Okay? So we basically choose these two values to minimize this quantity. Okay? This measures the deviation of the, the observed y and the fitted y, right? The y that we construct with this with our estimate. Okay? So we want this residual as small as possible. That is what we mean as good as possible. Okay? So we minimize this, but we don't simply minimize the sum of ui squared, because if you simply minimize the sum of ui squared, because there can be a positive residue and negative residue, and the positive and the negative values can cancel out each other. Right? So we minimize the sum of squared residuals. Okay, by choosing beta 0 hat and beta 1 hat. In this way, we obtain the estimates. Okay, and these estimates have the following formula. Okay? You don't need to understand the formula. You don't need to learn this by heart, but just having expression. Yeah. But at the end of the day, you have to the computer will tell you the results, so you don't need to remember this. Okay? It's typical. It just show you was how we can compute these two quantities, the estimates of beta 1 and beta 0, using the data xi and yi. Right? Here x bar is simply n 1 over n sum of I equal to n, and y bar equal to 1 over n sum of I equal to yn yi. So this x bar is simply the average of x, and y bar is the average of y. Okay, so this give us our the estimates of beta 1, and this give us the estimates of beta 0. And here, from this procedure, it justifies its name, right? Ordinary least square. So it's squared, and we minimize it. So it's called ordinary least square method estimates, or S estimates. Okay. So in the Coursera MOOC, I think there's a video talking about the derivation of beta 1 and beta 0 hat. Okay, so if you think you can handle that, you can watch that. But it's optional. Okay, in case you feel that you can understand all things, it's good. But if you don't understand everything, how we obtain this beta 1 and beta 0 hat, basically you need to remember, or you need to know the procedure, the idea. Right? The idea is basically minimize the residual squared, and how this residual is constructed. It's constructed from beta y minus beta 0 hat minus beta 1 hat times x. Okay. So by far we don't know beta 0 hat and beta 1 hat. So this u is a function of this beta 1 hat and beta 0 hat and beta 1 hat. Right? And now you can choose beta 0 hat and beta 1 hat to minimize this quantity, the sum of squared residuals, so that you can derive this beta 0 hat and beta 1 hat finally. Okay, so this is the procedure, or the idea, how to do ordinary least square estimation. Okay, so this graph illustrates the idea maybe. Okay, so here we have this fitted regression line. Okay, so this is y hat equal to beta 0 hat and plus beta 1 hat times x. Okay? And the actual xi and yi is this points here. Okay? So suppose for this point, xi, yi is this point, right? But the fitted value is here, so we have a residual ui hat. Okay, so the least square, the principle of ordinary least square is basically choosing this line. This line can have different, slopes and intercepts. Yeah, this is the intercepts. This is the intercepts beta 0 hat, right? And the slope is beta 1 hat. So this is one possible fitted regression line. There can be another one like this. So you have another intercept and slope. So you can choose different do this. So you may have a different choice of determining the regression line. Okay, but you can finally choose this one because it minimizes the residual sum of residual squared. So that is, this thing, sum of these residuals squared, that is minimized. Now again, we look at some examples. So here we consider the population of chief executive officers. And here, this y variable, the dependent variable, is a CEO's salary in thousands of dollars. Okay, and this x variable, or the explanatory variable, or the independent variable, is the average return on equity of the CEO's firm, okay, in the previous 3 years. So recall that ROE is a very useful measure or very useful ratio from your corporate finance class, right? Return on equity. If the return on equity is higher, which means that the performance of the firm is higher. So we postulate that first, the CEO's salary and the ROE of that firm has this linear relationship. Okay, so their relationship can be represented by a linear function. Moreover, we postulate that this beta 1 parameter, okay, is greater than 0. Right? Because the higher the ROE, the better the performance and the better for the company. So the CEO should be rewarded for good performance. Okay, so and we collect data on 209 CEOs. Okay, I will show you maybe in the next video. We have this data on 209 CEOs for the year 1990. Okay, and also have the ROE data for their firms. And we'll put this data together and apply this formula. We have all the y's, right? This, which is the salary, and the x's are the ROEs of the firms. So we can just put data into this formula and also this formula. We obtain that beta 1 equal to 18.501 and beta 0 hat equal to 963.9 191. Okay, so this is the intercept, which I have said is it is not very important, and this is beta 1, and tells you that if the return on equity increased by 1%, the salary is predicted to change by 18,500 and 500, right? And if so, basically, if the ROE is higher, the salary of the CEO is also higher, right? So now we ask whether this 18,500 has a causal interpretation, okay? By which, again, we mean whether it satisfies that the conditional expectation of U conditional ROE whether this condition is whether this condition holds or not. Right? So so if consider this U to be debt, then it's most likely that debt is uncorrelated with ROE. Okay? So if it's the case, then uh, this assumption holds. And if this assumption holds, we can see that this beta 1, this 18.5 that we estimated from data is a causal effect of ROE on salary. Okay, this is the example of CEO salary and return on equity. So, so notice that uh, the beta 0 hat and the beta 1 hat that we estimated is just our guess. Okay, it's a fitted line, fitted regression line that is best fitted the data, right? So as it minimizes the sum of residual squared. But the true regression line is not known. Okay, we're only guessing that this might be the true one, but the true one may be uh, the true regression line may be the dotted line. Okay, but given the data, it's the best guess. Okay, so another example is this wage and education relationship, the simple wage equation. So in this example, we have data on 526 workers in 1976. We have a bunch of workers and we record their wage and years of education. And again, we put this data into the regression formula. This one, okay, put x to be the education and y to be the wage, hourly wage. Right? From this, we get these two numbers, the beta 0 hat equal to negative 0.9 and the beta 1 hat equal to 0.54. Okay, so it says that in the sample, one more year of education was associated with an increase in hourly wage by 54 cents. However, here, uh, whether or not this estimated beta 1 hat has a causal interpretation is questionable. Again, we have argued that this residual term, this error term, may contain the innate ability of a worker. And we have discussed that it is possibly that the education and the ability is correlated. So conditional on certain level of education, the variation of one's ability might not be equal to 0. So, so more intuitively, if education is higher, it is also associated with higher ability. Okay? So both can contribute to a higher wage. So we cannot identify uh, whether the increase of wage is attributed to the higher education or higher ability. Okay? So we cannot actually identify a correct number of beta 1 just by this simple regression, because this assumption typically does not hold. Okay, so this is the condition that we have discussed. Expectation of u conditional x equal to 0 is very crucial for us to correctly apply simple linear regression model. Okay. Here's another example in which we study the relationship between voting outcomes and campaign expenditures. Okay. Here we have data on election outcomes and campaign expenditure for 173 two-party races for the U.S. House of Representatives in 1988. There are two candidates in each race, in each election race, A and B. Okay, one from the maybe from the Democratic, the other from the Republican. Vote A is the percentage of vote for candidate A, and share A is the percentage of campaign expenditures of candidate A. Okay? And again, we just put all the numbers, this vote A, data on vote A and share A into the OLS formula. We obtain the estimates beta 0 hat equal to 26.81 and beta 1 hat equal to 0.464. Okay? So it basically tells you that if candidate A's share of spending increase by 1 percentage point, then he or she receives 0.464 percentage points more of the total vote. Okay? So this is another example. So here we study the properties of OLS estimates. Okay, so again, when we we have know how to compute this beta 0 hat and beta 1 hat. So given beta 0 hat and beta 1 hat, and we can construct this yi hat, which is called the fitted value or predicted value. Which equals to the beta 0 hat plus beta 1 hat times xi. Okay? And then we can compute the so-called residuals or the deviation from regression line. the actual yi is what we observed, and this yi hat is actually computed by using the OLS estimates beta 0 hat and beta 1 hat. Okay? So we get this deviation of ui hat. So for example, this is the fitted line, right? yi hat equal to beta 0 hat plus beta 1 hat times x. Okay? And this is one of the, for example, for this xi, we have this yi hat. And the actual yi that we observe is this one, and their difference is the residual ui hat. And there are several very useful properties of this ui hat. First of all, the deviations from regression lines sum up to 0. Okay? We will have this on f if we compute the average of this ui hat is equal to 0, or the sum of this ui hat is equal to 0. Okay? Second, the sample covariance between deviations and regressors is 0. Okay, this is the regressor, this is the deviation or the residual. Okay, the sample correlation, which equals to the sum of xi times ui hat, equal to 0. Third, the sample average of y and x lie on the regression line. That is y bar, which equal to the well, n sum of I equal to 1 to n y of I. And this x bar is the sample average or sample mean of x. Okay, so the sample mean of y and x lie on the regression line, the estimated regression line. Okay, so here's the example of CEO salary and ROE. Recall that we have computed that in this example, we have obtained that beta 0 hat equal to 963 and beta 1 hat equal to 18.5. Right? So this ROE is dx, and the salary hat, for example, this one equals to the 963 point something plus 18.501 times 14.1, okay, roughly equal to this one. And similarly, we can construct the y hat in the same way. Right? And the difference between the salary that we observed and the salary hat is the U hat, right? The residuals. Okay? This is the residuals. For example, the difference between this one and this one. Y salary minus salary hat. Y minus Y hat. Okay? So once we have the regression line, we have the simple linear regression and estimated beta 0 hat and beta 1 hat, we ask ourselves how well does the explanatory variable explain the dependent variable. Okay? In the sense that whether x is kind of predictive about y. Okay? So what we do is basically we compare, first of all, these three measures of variations. First of all, we look at the total sum of squares of y. So it measures how the variability of y. It's very similar to the formula of sample variance. Right? If we have this 1 over n minus 1, then we got the sample variance of y. But here we got the total sum of square of y. Okay? It measures how the variability of y. And then we compute the explained sum of squares. So what is the explained sum of squares? It is basically y hat minus y bar squared and sum it up, okay? And sum them up. So it represents the variation explained by the regressions. Okay? So because this part is constructed by using information of x, right? So this part yi hat is actually predicted by x. Okay, so the total variations of yi hat is thus called the explained sum of squares. Okay? And for the rest part, the residual sum of squares is basically the sum of residual squared. And it represents the variation that is not explained by the regression or not explained by the x. Okay? And these three variations have this relationship: the total variation equal to the explained part plus the unexplained part. The explained part is the sum of explained sum of squares, okay, plus the residual sum of squares. Okay. And the goodness of fit measure, which is the r squared, basically equals the explained sum of square divided by total sum of squared, or it also equal to 1 minus residual sum of square divided by total sum of squared. So here, because so here we get SSE explained sum of square equals to SST minus SSR. So here we have this equal to SST minus SSR divided by SST. So we have SST divided by SST divided by minus SSR divided by SST. And this equal to 1. Right? So we have this formula. So here we see that if we apply this formula, okay, if we apply this formula here and also these formulas here, we obtain that in the CEO salary and return on equity regression, the R squared equal to 0.0132, which says that the regression explains only 1.3% of total variation in salaries. That is, ROE, okay, return on equity explains 1.3% of the variation in salaries. Okay? Basically, it means it's the explanatory power of ROE on CEO salary is kind of small. Okay. On the other hand, if we look at the voting example, the R squared is equal to 85.6%, right? So basically, it says that this regression or share of campaign expenditure explains 85.6% of the total variation in election outcomes. Okay? So one thing that is very commonly confused in the practice, okay, is that people, a lot of people pursue a very high R squared in their regression, but actually a high R squared does not necessarily mean that the regression has a causal interpretation. Okay? So high squared is a good thing. It means that the regression line fit the data very well, but it does not necessarily mean that y and x has causal relationship. Okay. So if we look at the wage example, it's not here, but if we look at the wage example, uh, if we run regression, actually we will get a very high R squared. Okay, but we have discussed that in this regression equation, typically the estimated beta 1 hat using OLS method cannot correctly identify the causal relationship between education and wage, right? Because we don't have this, we don't have the crucial assumption, the conditional mean of u conditional x equal to 0.